The goal of this video is for you to get a thorough understanding of how to use TensorBoard to easier understand, debug, and modify our models. This is a long video because there is so much to cover when it comes to TensorBoard. So let me first of all show you an overview of the things we're going to learn how to do in this tutorial. We're going to start off learning about what is perhaps the most basic, but also probably the most useful thing, which is obtaining these accuracy and these loss plots. And in this example right here, you see the accuracy plot when training our model with varying learning rates. And then we're going to move on and learn about how to visualize images. So in this example here, we're performed some minor data augmentation in turning a very few percentage of the images to grayscale. And so visualizing these changes can be very useful to make sure that what we intend to happen is actually what is going on. So for example, here we have a horse that has been converted to a grayscale image. Also, we're going to see how to both create and plot these confusion matrices to TensorBoard, where we have the predicted label on the y-axis and then we have the true label on the x-axis. In this way, we can see what and where the model is misclassifying images. So for example, here we have that it correctly predicts airplane 65% of the time, but in 7% of the time, it's misclassifying a bird as an airplane. Also, we can see that it predicts cat correctly 40% of the time, where the largest mistake happens when it misclassifies it as a dog in about 21% of the cases. Other useful things is that you can visualize the graph of our model. So here we have a very simple model which takes in two inputs, x and y. It performs a matrix multiply and then sends that through a ReLU, and that will be the output of the model. And so this can be useful if you're building more complicated or complex models like ResNets, where you want to make sure that all of the skip connections are at the correct places. Or if you just want to get a better understanding and see more visually how the model looks like. Other cool things that you can do with TensorBoard is that you can visualize and see the distribution of the various parameters of your model. So this can be useful to debug if you get error messages and you want to see exactly where in the model the error is occurring. Then these distribution plots can be useful to know which layer the fault lies in. But we also have a lot more things to look at. So we're, for example, going to do hyperparameter search using the HParams API of TensorBoard. With this, you can see what parameters to use for your model by seeing the different correlations between, in this case, the dropout, the learning rate, and then the number of units, and then how that finally corresponds to the accuracy after a single epoch run. So to easier understand this right here, we can restrict our attention to only looking at what corresponds to the best accuracies. And what we can see here is that the model preferably wants quite low dropout, and then it wants a very high learning rate and also high number of units. So in this case, we're checking the accuracy on the training set. So that's probably why it wants very low levels of dropout. Then we are also going to learn how to use the Projector tab of TensorBoard, which is pretty awesome visually. And you can use different algorithms like the TSNE and then the PCA to get an understanding of how your model is learning to represent these images projected down from a very high dimensional space to 3D where we can easily visualize them. For example, here we are running it on the MNIST dataset. And we can, for example, use the TSNE algorithm. And if we, for example, now search for, 0, then we can see that there are clusters of that 0 right here. And similarly, if we would search for 2, we would see that there's a cluster over here of the number 2. And so this can be useful to understand how the model works and also how the model creates its representation. The TensorFlow Profiler is also a very useful tool that allows you to see what is taking up the most amount of time and sort of what aspects you should aim to improve in your training. So for example, here we're given a summary of the different parts and how much time it takes out of our training. So for example, in this graph right here, we can see that the input is taking a very big part of the time. And so what they also do is give you some recommendations. And they say that the program is highly input bound because about 84% of the total step time is waiting for input. And so what we should try to focus on in this particular program is improving the efficiency of our input pipeline. And there are also other parts of the profiler where you can see many different other parts as well, but more on that later. Now you have an idea of the different parts and areas of TensorBoard that we're going to cover. So let's get started. Alright, so to make this video at least relatively well structured, I've divided it into different files where for each file we're going to focus on one specific part of TensorBoard. And for each of them I have a starter code, and my thinking is that I'm going to go through the starter code, which is based on code from many of the previous tutorials I've done. So I'm going to go through it relatively quickly, and then you can check out the previous videos. I'm going to refer to those to go into more depth in each of the different parts. But so we're going to base everything from the starter code, and then we're just going to modify it or add some parts to write to TensorBoard. So to start off with, these are the basic imports that we're going to need. And then this is what we've seen previously. We're going to add those two lines just to avoid any GPU errors. We're loading the Cypher10 dataset from TensorFlow datasets. We're normalizing those images by dividing by 255. And then we have some data augmentation on those images. So then we do the mapping and the cache, and then the batching and prefetching on those training and test set. Although we're not shuffling on the test set. And then we have the class names right here, and these are used later on in the Projector tab to see the correct label for each respective image. Then we have a model right here, very simple model using conv layers, 2 conv layers, a max pooling, a flatten, and then 2 dense layers with a dropout in between. And then right here we have some setup for custom training loops. So we're getting the model first of all, then we have the loss function, we have the optimizer, Atom in this case, and then we have a accuracy metrics to keep track of the current accuracy. And then we have these 2 train writers, which is what we're going to use to write to TensorBoard. And these are going to be train and for the test. So for each of them, we're going to keep track of a step for the train step and the test step. All right, and then we have custom loop, where we're going through for epoch in range of num epochs, and then for batch index in DS train. And then, so this is pretty basic. We're doing forward propagation, backward propagation, and then we're doing gradient descent or an optimizer step right here. Then we're doing the same thing for the training set, although we're not doing back propagation, we're just checking what the accuracy is. All right, so for this first file, I'm actually going to do something that may look a little bit weird, but we're going to remove a lot of this code. So we're going to go just to here, I think. And so the idea here is that starter code is what we're going to base pretty much every of those files you can see right here. But this specific one, we want to use callbacks. And this is a more simple way where we're not using custom training loops. So I want to show that first. And so after we get the model, we're just going to do model.compile. We're going to specify our optimizer. In this case, we're just going to use Atom. And then we're going to specify the loss. In this case, we're going to use sparse categorical cross entropy, and then from logit equals true. We're also going to specify the metric, which in this case is going to be the accuracy. All right, and then we're going to do TensorBoard callback. So this is perhaps the most simple way to use TensorBoard, and I'm going to show you exactly what it does, but it's very convenient. So all you have to do is you need to do keras.callbacks.tensor board, you got to specify a log directory where it's going to keep track of all the logs. And so let's just do that. Let's call it TB callback directory. And then we specify some histogram frequency. And this is just, we're going to set that to 1. And that is for the distribution plots of the gradients and all of that stuff that I showed you previously. All right, so lastly, we're going to do the model.fit. So we're going to send in the DS train. We're going to send in a number of epochs, let's say, I don't know, 5. Then we're going to do validation data. We're going to send in the test set, actually. I mean, normally you would, let's just, for illustration purposes, let's just pretend the test set is the validation data. I know this is very incorrect to do, but so normally you would split the training data into a validation data and then send that in. But that doesn't really matter for this purpose. And then we're going to specify the callback. We're going to do TensorBoard Callback. And then we're going to specify verbose equals 2. All right, so that's it. Let's run this, and I'm going to show you then how it looks like in TensorBoard. But actually, before we do that, I have to show you how you would actually run it. So how you would run this is you would go to the folder where you have that specific, where you're running the specific script. And then you're gonna also have activated the environment that you have TensorFlow on. And then you would do TensorBoard, you would do logdir, and then you would specify the one that you called right here. So TB callback directory. And if we run that, we're gonna get back a URL, which is localhost 6006 in this case. And so if we go to that and we update it, we'll get something that looks like this, where we have the training and then the validation accuracy for each epoch, and then we also have it for the loss function. So as you can see, which is perhaps a little bit strange, we have that the validation accuracy is actually higher, but just keep in mind that we're using dropout, and then we're also using and we're also using some data augmentation, which might make it more difficult for the model to overfit on the training data. So just for example, we're converting some of them to grayscale. And of course, that could be quite more challenging. So that's probably why. Normally you would see this in reverse, that the training is higher than the validation. All right, but as we can see right up on this tab right here, we have 4 different ones. So that's just for the scalars. That's just for the loss and the accuracy. You also have the graph that sort of tells us how it looks like, right? We have our input, 2 comb layers, max, pool, flat, and dense, dropout, and then another dense. So you can inspect it right here. Then we have the distributions that I showed you previously, where you can see the gradients of all of the parameters, or rather the distribution of the parameters. All right, so that's the most basic way to set up TensorBoard using callbacks. And what I'm gonna move on to is show you how to do it from custom training loops. And so that's what we'll be working with from now on. But just know that most of the things that I'm gonna show you, you can also do using callbacks and using model.fit. But using custom training loops allows us to have more flexibility and makes a lot of things actually more simple to do. So let's do full screen on this. And again, this is just a starter code that you saw previously. And all that we're gonna do is we're gonna move down to the part where we have the custom training loops. And here we want to now add so that we're printing to TensorBoard. And so one idea could be that either you're writing it to TensorBoard for every batch, and so you could do it here. You could do it right here after this. That would work, but perhaps it would be a cleaner graph if you do it every epoch. So what we could do is right here, we're going to do with train writer as default. Then we want to send in the loss, and we also want to send in the accuracy. And just one thing right here is that we're gonna send in the loss, just like this, and this is actually just going to be the last loss of that batch. So just a note, you would probably want to send in the mean loss over that batch, and so you would have a list of the losses, and then you would take the mean of that and send that in. But this works just to show how you can write to TensorBoard. So we're going to send in the loss right there, and then we're going to set in step, and we can use the epoch as our step. Then we're going to do the same thing, dot scalar. We're going to do it with with accuracy. So let me scroll down. We're going to do it with send in the accuracy, and the accuracy are going to be stored in this accuracy metric dot result. And keep in mind here that that's reset in between the epochs, and it's also reset in between the training and the testing. So this should be iterate through the test set. All right. And then we're going to accuracy metric dot result. We're going to specify the step again as epoch, and then that's it. So now we've done it from the training. We also want to do it for the test. So what we could do here, since we're going to do pretty much the same thing, we could just copy that and paste that in. And we got to make sure that we're changing all of this stuff. Test writer step is still epoch, step is still epoch. And yeah, so that should be it. Hopefully there are no mistakes in this right now. So one thing to keep in mind here is that we're now using another log directory. So here we're using logs, and in logs we're storing two subfolders for the train and the test. So let's run this first of all, and again we're gonna open up this this Anaconda prompt right again, and we're gonna use this, but we're gonna specify the logdir to instead be just logs, and then it's automatically gonna find the training and the testing. So if we run that and we then go to Firefox or your browser and go to TensorBoard on that URL, localhost 6006. And I guess we just have to wait a little bit here because it's gonna write every epoch. So, all right, so here we can now see the accuracy plot, for example, and also the loss plot. And these are going to be very, clear, discrete steps because we're just recording it every epoch. But of course you could, as I said, do it every batch, and that would give you a much smoother graph. But what is perhaps a little bit odd here is that the test set has higher accuracy than the training, and I would imagine that has to do with the augmentation I chose to do. For example, I made some of the RGB on the training to grayscale, and that is of course going to make it a lot harder for the model to train on those. So that's probably the reason why. So that's what I pretty much wanted to show you on that. You could also do more complicated or more complex things in that you could, for example, use it for hyperparameter search. You could do something like for learning rate and then you could specify the learning rates you want, something like this. And then let's just indent that one step. And so what you could do then is you could sort of train a model for a specific number of epochs with each respective learning rate. And here I'm using a grid search just on those 5 different learning rates. So let's do that. We can do train step equals test step, and we're just going to set that to 0 every time. And then we're going to do the train writer is tf.summary.create file writer. And then we're going to do logs train. But then we're also going to add, we're also going to add string of learning rate, just to make sort of, we can distinguish between the different runs. So let's do that again, and let's do the test writer. And here we're going to do test. And then we need to get the model because we want to sort of reset the weight for each time. So we're going to do get model. Then we're going to do optimizer is keras.optimizers.atom. So we're also we need to reinitialize the optimizer with this specific learning rate. And then you could do it this way. You can write the test writer like this from some epochs, but let's just do it for every batch, as I said. That might make for a smoother graph. So what we're going to do here, we're going to specify the train step rather than the epoch. And then after here, we're going to iterate up the train step by 1. And that's going to be sort of one discrete step in the plot. And then we're going to do that for the test writer as well. So we got to change this to the test step. And we got to do it for all of these to make sure that we don't do anything wrong here. We're going to iterate up that by 1 as well. All right, so let's think, is there anything else now we need to change? We could decrease the number of epochs just to make it faster. So let me run this and I'll show you what it looks like in TensorBoard. All right, so looking at the TensorBoard right here, I've just separated out for the train. So you could just write train right here and you can get all of the different ones, and these correspond to different learning rates. And you can also do some smoothing right here. So you can get, the loss just varies a lot from batch to batch. And so you could use some smoothing to make some better looking plots. And then, so for example, just in this case, if we compare, we would have that the learning rates, the initial learning rate should probably be between 0.001 and then 0.0001 between this orange and this red one right here. And so that's it for sort of getting loss plots and accuracy plots, and you can play around with that. And you can, that is very, very useful. So let's move on to getting images. So what we're going to start with right here is just visualizing images. And probably the first thing we're going to do here is we're going to add some data augmentation. We're going to use matplotlib, and to plot it, they want values between 0 and 1. So we can, matplotlib wants values. So what we can do is we can do image is tf clip by value, image, and then clip value min is 0, clip value max is 1. And so by the way, if you're wondering why it would be under or over this 0 and 1 range, since we divided by 255, that should be the natural range. But because of this data augmentation, some pixel values can become lower or greater than 1. So we just want to make sure at the end that they are actually between 0 and 1. That's going to be used later on, but I'm going to show you why in just a moment. So what we could do here is we could actually remove the training part. So we could just do for batch like this. And what we could do is we could iterate through for batch xy in enumerate ds train. And so what we're going to do, first of all, is we're going to create a figure and we're going to create an image grid. So we're going to send in x and y to that, and then class names. So this right here is a function we're going to create in this utils function right here. But we're going to create an image grid, and then we're going to do with writer as default. We're going to do tf summary.image, and we're going to send in visualize images, and we're going to do plot to image, and we're going to send in the figure, and then the step is just equals to step. And so we could, in this case, we're just going to just have a single writer and do it like this. And instead of using train step, we're just going to call it step like this. And then that's pretty much all we're going to do. We're going to iterate up step by 1. All right, so this is how it's going to look like in this file. But of course, we need to create this image grid, and we need to create this plot to image. I just want to say, first of all, that there are easy ways to do this. And what I'm doing here, we're going to create this image grid and this plot to image, is unnecessarily complicated, but it helps or rather, if you want it in a clean way so that you get it in a grid and you get it with the labels above it and so on, then this is how you're going to want to do it. There are easier ways to just plot the images, but they don't look very nice. And of course, we want it to look nice. So let's go to utils, and what we're going to, first of all, is I'm just going to copy in some imports that are going to be used in this file. And the thing we're going to do first, so we had, let's see, we had the define plot to image, and we're going to send in some figure. So let's do pass on that first of all. And then we had another image, another function. So we had image grid, and we send in some data, we send in some labels, and we send in some class names. And what I'm going to do is I'm going to copy in from TensorFlow official tutorials this plot to image. So this is stolen from TensorFlow official guide. You can see the URL right here. But essentially, so it converts the matplotlib plot specified by figure to a PNG image and returns it. This applied figure is closed and inaccessible after this call. So basically, it's converting the matplotlib plot into a PNG in memory, and then it gets decoded to a tensor, which can then be sent to the TensorBoard. So here we're using IO to save the plot in memory. Then we're closing the figure, preventing it from being displayed directly inside the notebook, and then we're converting PNG buffer to TF image by image.decode PNG, and then lastly we're adding the batch dimension. So, I mean, I don't want to focus too much on this. This is not really relevant, I would say. This is just some boilerplate code just to make sure that it's in the right format, which is a tensor. And then this image grid is what we're going to do first. So we're going to create the image grid, which is going to create this matplotlib figure. Then we're going to send it to this plot to image, and that's going to then be sent to TensorBoard. So first of all, the data should be in this format. So we should have batch size, H, W, and then channels. So what we could do first of all is we could just assert data.number of dimensions is 4. What we're going to do is we're going to create a figure. So figure is plt.figure of fig size, and this is just matplotlib, right? That's the import right here, import matplotlib.pyplot as plt. So we're creating that with a fig size of 10 and 10, and this is in, I think this is in inches, so it can be a bit confusing, but I've tried out different values, and this is just what looks nice. So, but anyways, the number of images are going to be data shape 0. I guess this is specific to sort of a specific batch size, the fig size that we're using here, and what I've tried for is batch 32. You can also use a larger batch size and it's still going to look relatively okay. What I'm doing here is that I'm creating the number of images to be data shape of 0, which is, you know, a general format. It's not specific to 32. Then we're going to do size is integer of np.ceil of np square root of num images. And why we're doing this is because we want a nice looking grid, a square grid. So the size of the grid is going to be the square root of the number of images, just sealed to the up one integer value. And then what we're going to do is we're going to iterate for I in range of data shape of 0. So for each image in our data, we're going to create a subplot for that one. And we're going to, the size of the subplot is just going to be size and size just for the number of images in total. And the specific image right now is going to be specified by this index, which is I+1. And the title of this plot is going to be class names, labels of, so the labels are the values of the index for that one. And then we're doing class names of that index right there to get the name of it. Then we're going to do xticks, and we're just going to send in an empty list. And we're going to do yticks, and we're going to do similar. And then we're going to do plot grid equals, or plot grid false. And then we're going to do if data shape of 3 is 1. We're going to do plotted, and we're going to do cmap is plt.cm.binary just to get grayscale, right? So if grayscale, this is what we're going to do. And if it's RGB, we're just going to do plot imshow of data of I. And then in the end, right, let's see, right there, we're going to return the figure. And here we don't have to specify any CMAP because RGB is by default. So this is a lot of matplotlib, and I don't want to go into the specifics of that, but you get the general picture right here. Even if you're not too familiar with matplotlib, I would think we're creating a figure, and then we're creating a subplot, which are going to be these specific training images, and the size of it is size. So the number of rows is size, and that is dependent on the number of images that we send in. So let's say we send in 16 images, then the grid is going to be 4 by 4, and each of those cells in that 4 by 4 grid is going to be an image from our training set. So now we have the image grid, and then we have plot to image. So if we go back, this should most likely work now. So we're doing first image grid, then we're doing plot to image, and here we're writing every single image in our batch. So that wouldn't really be necessary. Perhaps you want to do it every epoch or something, but this could be useful just to check all of the images. So let's run it and let's see what it looks like. All right, and then right here we need to import it, right? So we need to do right here, we need to do from utils import plot to image and then image grid, and rerun it, and hopefully it works. All right, writer as default is not defined. So I think this should be writer dot as default. All right, so if we open up the TensorBoard now, we get it in a nice format. We get the labels printed above it. And as you can see here, this is a square grid. So for example, here it's 6 by 6, and then these last ones aren't covered by any image. And that's because we did that seal and rounded it upwards. But I would say this looks pretty good. This is a nice way to visualize the images. And then you can see the step right here for each of the batches. One thing here is that if you scroll back just one, you're going to see that it's actually 6 steps. And when you call in Anaconda, you call TensorBoard, you have another argument you can send in, which is samples per plugin, and that would specify how many images you want in this step slider right here. So for example, if you just specify it, so if you specify that, for example, to 94, then that would mean that one slide step right here is for one batch, rather than jumping, in this case, about 25 batches. So that's just one thing to keep in mind if you are wondering about that. But anyways, that's how we can visualize images. Now, the next thing is we want to create this confusion matrix. And this is also a little bit complicated, but as you saw previously, it's going to turn out pretty good. So let's go through it step by step. And again, this is the starter code as usual. How this is going to work is that normally you would create the confusion matrix by sending in all of the images at the same time or rather the outputs and the Y labels at the same time. And then that would create a confusion matrix. But in this case, we're creating it, or rather we want to update it as we do it for every batch, right? Let's say we have an enormous data set. We can't send it in at the same time. So what we're going to do is we're going to create a confusion matrix that is initially empty. So we're going to do empty zeros and then length of class names and then length of class names, right? That's going to be the number of rows and the number of columns. And what we're going to do is we're going to update this throughout going through our batch. So we're going to go through here and we're going to do confusion is plus equals a function get confusion matrix. We're going to send in y prediction, and then the class names. And that's going to then add up to that confusion matrix. And we might get some numerical roundoff errors and so on, but at least this approximation is very good, and it's going to be enough to get a good representation of what the model is learning. Then after that batch, we're going to do with trainwriter.asDefault. We're going to do .tf.summary.image, and we're going to send in, we're going to specify the name, which is confusion matrix. Then we're going to do plot confusion matrix. And again, this is going to be another function. And we're going to send in confusion, and we're going to divide by the batch index because we're going to get a confusion matrix here at every update that is going to have its own probabilities between 0 and 1. But because this is a linear operator, then we can divide by the batch index, and we will get an average of the probabilities for the entire epoch. Of course, you could get overflow by this, since you're essentially, let's say you're adding 1 every single batch, but to get overflow, you would need to have an enormously large data set. Even if you have 100,000 samples, having 100,000 is very far away from overflowing. So this is okay. Just keep that in mind though. And then we have class names. And then we're going to specify the step as the epoch. So we're just plotting the confusion matrix every epoch, because this can also be quite expensive. All right, and then we don't have to do it for the test set, but of course you can do it for the test set if you want. But I'm just going to remove this actually, like this, because that's not really needed, and we can save on some compute. So what we want to do now is we want to go to the utils function, and we want to create those two functions. All right, so we're gonna first do get confusion matrix. We're gonna send in y labels. We're gonna send in logits. We're gonna send in class names. So this right here are the correct labels. This is just what the output from the model is, and these are the class names. So let's do pass on that just quickly, and then we also want to define plot confusion matrix. And here we want to send as input some confusion matrix, and I'm just going to write CM, and we're also going to send in some class names. So maybe first of all, we want to actually create the confusion matrix, and to not do this from scratch, we're going to use sklearn to produce the confusion matrix. Creating confusion matrix would be a separate video, I guess, but we would do the predictions are the numpy argmax of logits, and then x is 1. So we're converting it to numpy here as well. Sort of going from numpy to TensorFlow is pretty seamless. And so we just have to do numpy argmax directly, and then that will be the predictions. Then we're going to do the confusion matrix is sklearn.metrics.confusion matrix. And we're going to send in the y labels. We're going to send in the predictions, and then we're going to send in labels as np arrange of length of class names. And this is essentially to make sure that we're getting a confusion matrix which is length of class names in both the rows and the columns. Because let's say we have a batch size of 32, we would not perhaps get one example from each class every run. And that would destroy our confusion matrix. So we're sending this in just to make sure that it's actually the size we want. And then we're just going to return the confusion matrix. All right. And then we want to do the plot confusion matrix. And what we're going to do here is we're going to do size is the length of number of class names. We're going to create a figure, which is plt.figure. And then fig size is size comma size. We're going to do plot.imshow, and we're going to send in the confusion matrix. We're going to do interpolation is nearest, And you can read documentation for what this is exactly doing. I'm not entirely sure what the different interpolation algorithms are, but this seems to be a default one. And then we're going to use cmap is plt.cm.blues. So this is just going to make the sort of the color of it blue. We're going to see exactly how it looks like later on. But then we're going to plt.title. We're going to specify the confusion matrix. And then the indices are going to be np_arrange of length of class names. All right. And then we're going to do plot.xtics. We're going to send in the indices. That's how many sort of x values, how many ones we're going to have. And then we can specify the names of them, and we're going to do class names. And then to have them look in a nice way and so that the text don't overlap, we're going to specify a rotation to be 45 degrees. And then we're going to do yticks, and we're going to do indices and then class names. All right, and then we want to make sure that we normalize. So we want to normalize confusion matrix. And how we do that is we do cm is np.around. We're going to do cm as type float. And we're going to divide by cm.sum axis 1. And we're going to do np.new axis. And we're going to specify the number of decimals. So this is just to make sure that everything adds up to 1. For the sort of the predictions for a specific one can only add up to 1 over all of the different labels. So that's what we're doing there. Then we want to print, so we want to have the text of the probability for that specific one. So we're going to first do threshold is cm.max. Then we're going to divide it by 2. And we're going to do something pretty cool with this, but you're going to see it in just a second. So we're going to go through for I in range of size. And then we're going to do for j in range of size, right? We need to go through every row, and then we need to go through every column. And we're going to do first color is white if the cmij is greater than the threshold, else black. All right. So if it's over some threshold, then we're going to make it white, because then the background color of that cell is going to be relatively dark. So then we're going to make it white. Otherwise, if it's lower, then it means it's relatively light cell, or a light colored cell, sort of more white cell. Then we're going to make the text black. And then we're going to do plot.text. We're going to specify the position as ij, and then we're going to send in the actual value, which is cmij, and we're going to do horizontal alignment. We're going to do center, just to center the text, and then we're going to do color equals color, and that is the thing we specified over here. All right, and then after that, we're going to do plot tight layout, and this is just to get some nice format. And then we're going to do plot x label, and we're going to do true label as the x values. And then the plot.y label is the predicted label. And similarly, as we did before, this is now a matplotlib figure. To get it nice to TensorBoard, it needs to be converted to a tensor. So we can reuse the plot to image. So we can do plot to image of that figure, and then we can return CM image. All right, so now we can go back, and hopefully this should now work. So if we run this now, this is not going to work actually, right? We need to import this stuff as well. From utils, import, what was it called? Get confusion matrix, and then plot confusion matrix. And hopefully that will run now, so let's see. All right, so as you can see here, it seems to be working. Of course, we have only run it for a single epoch now, so our model is quite bad, and this is represented, of course, in the values of the diagonal, which is how much, the probability of it accurately classifying each specific class. So in this case, airplane, about 50% and so on. So, I mean, let's let's increase the number of epochs, let's say to 5, and rerun it, and then you'll see as this improves over the epochs. All right, so as you can see, it's become better. The model is still pretty bad. We're using a very small model, and so you can still see that it's not perfect. But anyways, the visualization seems to work. Let's now move on to doing a graph. So this is going to be, I guess, a little bit simpler. So let's see here. I'm actually not going to need anything of this. So we're going to remove all of the data set stuff right here. We're going to remove all of it. So the thing we're actually going to do is we're going to do writer, and we're going to do tf summary create file writer. We're going to specify logs, and then we're going to specify graph viz. Let's just call it that. And then we're going to just define some function. My function, it's going to take x and y as input. Then it's going to return tf.nn.relu, and then tf.matmul, and then x and y. Right? So it's just doing matrix multiply and then taking the relu of that. And we're going to do x is tf random uniform shape 3x3. And y is just similarly tf random uniform 3x3 as well. And then we have to create, we need to do at tf.function. So since TensorFlow 2.0, eager mode is executed by default, but creating these graphs is actually not possible to do in eager mode. So we need to make sure that it's run in a static graph. And so this at tf function makes sure that the function is converted and run in a static graph. And when that is done, we're going to do tf.summary.trace on, and we're going to do graph true profiler true. Then we're going to do out is my function of that x and y that we just send in. Then we're going to do with writer as default. We're going to do tf summary.trace export, and we're going to do name. We're just going to call it function trace. We're going to do step equals 0 because we're just doing it once, and then profiler out directory is going to be logs, and then we can't do it in this way, so we need to do it like this. Just a weird thing that we need to do, and then graph visualization. And let's see, we also need to do it like this, if I recall correctly. And that should work. Now, if you want to visualize a model, this is still going to work. So, I mean, if you have a model, just to return model of X here. So just create your model here using chara, sequential, and so on. And then just do return model of X. And that should still work. What I want to do here is just show you a very minimal, simple example. But of course, this can be used in general. So if we run this and then go to TensorBoard, or let's see that it's no error first of all. Yeah, so we get some warnings here, and I'm not really sure what to do about them. I mean, sometimes in TensorFlow you just get errors, but if stuff works like it should, then I don't know. I don't know what to do about this. Anyways, we're just gonna look at the graph, and it's gonna look no data set name train. All right. And then we have this x and y matrix multiply relu, and then that's the output. Sometimes these graphs can look a little bit weird. Like, I'm not sure why we have two identity right here. But yeah. So anyways, you can see sort of the most relevant parts here, that we're doing this and then relu. And personally, I haven't used this too much, but it can be useful, I'd imagine, if you want to debug some very complex model. But anyways, let's move back to the code. So we're gonna want to do hyperparameters now. And this is something that's very useful, I would say, if you want to do hyperparameter search. And you get it visualized very nicely, so it looks very good. And yeah, so we're gonna again just work from the starter code, and we're gonna modify it. And the thing we're gonna modify now is we're gonna create sort of a function, and we're gonna call it train model. Let's see, 1 epoch, and then we're gonna send in something called HParams. And actually, we need to import that first of all. So what we need to import is from TensorBoard.plugins plugins.hparams import API as HP. That's just for the HParams API, and we're going to import it as HP. And so let's move back down to that function. And what we're going to do here is, let's just say in our model right here, we're going to copy in that model. And let's say we want to sort of play around with, when it comes to the model, let's say we want to play around with this right here. Let's just call it number of units in the dense layer right here. And of course, you could imagine doing this for different values and then so on. But I'm just going to use that for this example. And what I'm going to show you is how to get the HParams from that. And let's just say we want to play around with the dropout as well. So wait, let's remove this and drop out of some drop rate. And then let's also say we want to play around with the learning rate. So from this HParams, we're going to get units. We're going to do HParams, and then we're going to call it HP num units. We're going to get the drop rate. And of course, we haven't defined these, but we're going to do it later on. So we're going to get HP dropout, and then we're also going to get learning rate. And that is Keras optimizers.atom. The learning rate will be set to learning rate, and we need to get the learning rate as well. And that is from HParams HP learning rate. All right. So now that we have those, we have the oh wait, that's not the learning rate, optimizer. That's the optimizer, and we're using the learning rate that we got from HParams. And then we're creating the model using this units and this drop rate. Then we're gonna actually create one training epoch, and we're gonna do it with this. So we're gonna copy that and put it over here. Since this function right here, oh, not this one, this one, train model 1 epoch. This is going to train it for 1 epoch. So we can paste that, and that should be it. Then we're gonna want to write to TensorBoard. So write to TB. We're gonna do that by specifying the run directory. And since we're doing many different runs with different values of the learning rate and drop rate and so on, we're gonna first specify logs and then train, and then we're gonna do plus string of units. Then we're gonna do units. So this is just going to be an integer. Then we're going to be units, and we're going to underscore just to make it readable. Then we're going to do string of drop rate, and then we're going to do drop out. Then we're going to do string of learning rate, and then we're going to do learning rate. All right, so this might look a little bit weird. This is just not to get one line too long. So this looks all right. We can easily read it. And then when we have the run directory, which is going to be different depending on the units, drop rate, and the learning rate, we're going to do with tf.summary.create file writer of that run directory. We're going to do as default. So notice here that we're not using a train writer here. We're creating the file writer as we sort of write it. And that's going to be different for every run. Then we're going to do HParams of HParams, and we're going to do accuracy is accuracy metric dot result. So this right here is just going to record the values that was used for this run. And then we have the accuracy, and then we have tf summary dot scalar accuracy, and then we're going to send in that accuracy, and we're just going to do step 1. And then after that, we got to do reset the states of the accuracy metric. All right, now we can, I guess, remove this get model because we created the model for every run. Then we don't have to have that. We don't have to have the number of epoch, or yeah, we could have the number of epochs, but I'm actually gonna just run it for a single epoch anyways, so I'm gonna remove that. Then we want to have the loss, we want to have the optimizer, we want to have the accuracy metric, and then we don't need those because we're writing it already using a new writer every time. But then we're gonna specify HP num units. We're gonna do hp.hParam. We're going to do num units. That's what we're going to call it. Then we're going to do hp.discrete. And we're going to send in 32, 64, 128. So what this means is that we're choosing the number of units in that particular dense layer to be 32, 64, or 128. So we're kind of using, a kind of a grid search here. And if you are familiar with hyperparameter search, you probably know that using a random search is better. And I'm not going to explain why, but essentially using random search is better. And of course, what you would do here is that you would perhaps random sample the values first using random search, and then that's what you would put into these discrete values. But anyways, just for the illustration here, I'm just using it in a very simple way, in discrete steps, in a grid search manner. And then we're going to do HP dropout, and we're going to do hp.hParam. We're going to send in dropout. We're going to do hp.discrete, and we're going to specify 0.1, 0.2, 0.3, and 0.5. So let's say we have those 4 values. And then we have the HP learning rate. And let's do hp.hParam. And let's call it learning rate. And again, we're going to hp.discrete. And then 1e minus 3, 1e minus 5, and 1e minus 5, 4 and 5. So anyways, what you can also do here is that there's something called hp.int interval, and then I think it's real interval. And then you can sample from those. Yeah, I don't really see the point of those really. I would just sample from them myself and then find the values and then put that in as discrete values. So I think this would work well in general as well. But there might be some use case that I'm not really familiar with. So anyways, when we have those, we can change this right here. We're not going to use the normal training loop that we've used previously. What we're rather going to do is we're going to do for learning rate in HP learning rate dot domain values, and we're going to do for units in HP num units dot domain values, and also for rate in HP dropout dot domain values. In this way, we're just iterating through the learn rate, units, and the rate in these discrete values. Then we're going to run it just for a single epoch, but otherwise you would do, for epoch in range of the number of epochs right here. But we're just going to do it for one. So then we're going to do HParams is equal to a dictionary, and then we're going to specify HP learn rate is equal to learn rate. And what is wrong here? Yeah, it needs to be not equal to, like this. And then HP num units, we're going to specify that as units, and HP dropout is just rate. All right. And then we're going to call that function, which is train model 1 epoch of HParams. So actually one thing here is that you wouldn't do for epoch here, because that would sort of reset this. Yeah, what you have to do then is modify this. So you would have to add one loop in here, I would imagine. But anyways, this works just to illustrate how you would do it for a single epoch with different hyperparameters. This might take a while to run, so I'm just gonna run it, and hopefully we don't get any errors as I say that. All right, so we get the HParams right here, and I'm gonna just make this a little bit larger, and you're gonna see how it updates as it's getting more data points. All right, now we get all of these hyperparameters, and this might look a little bit confusing. So what you could do, let's see if I can do it. You can just specify sort of the top ones, the top accuracies, and in this case, we can see that the top ones correspond to having high number of units, right? A larger model is always better, basically, with a learning rate of 0.001, so the highest of the ones we chose, and then preferably with the lowest level of dropout. And again, this is because we're doing it on the training set. You would actually want to do it on the validation set to make sure that this is correct. But again, we just want to illustrate how this works in TensorBoard. So that's it for using the HParams. Now we want to move on to doing it the projector. And the projector is very cool and can be very useful. So let's move to that file, and we actually don't need these things. So I'm going to remove the model, and I'm going to remove, let's see, pretty much everything here. And we're not going to need anything really. We're going to need one batch, one X batch, one Y batch. We can do that by using next iter of dstrain. Then we're gonna send that to some function, which we're gonna create, plot to projector. We're gonna send in X batch, and we're gonna send in X batch again. I'm gonna explain this in a second. And then we're gonna send in Y batch. We're gonna send in class names. We're also gonna send in some log directory. We're just gonna call it proj, like that, projector. And so why we're sending in xbatch 2 times here is because this function we're going to create is going to obviously take in some data points, right? The images, and it's going to take in some labels. But it's also going to take in some feature vector. So normally you would have sent in your images, your data to your model, and then out from that model you would take some feature vector, which might be in some arbitrary number of dimensions. So then this projector is going to take in this feature vector and try to obtain a projection down to the images and see sort of what of the features, and use one of these algorithms like TSNE or PCA to project it down and see what does our model sort of think are in similar groups depending on what the feature vector says. And what we're going to do in this case is we're not going to send it into some model. So what that means is we're going to use the images itself. We're going to reshape the images to just be one long feature vector with the pixel values for that image, and that's going to be our feature vector. So again, as most of the stuff in this tutorial, it's been for illustrating how to use TensorBoard. So this is how to make it simpler for us, but normally this would be a feature vector. So just to be ultra clear, you would do feature vector, you would do model of xbatch, you would get some feature vector, and here you would call in with that feature vector. Now, we're not going to do that, as I said. So all we need to do is create this plot to projector. And before I forget, let's do from utils import plot to projector. And then we're going to go to these utils functions again. And we're going to need 2 things. So first of all, we're going to need something called a create sprite image. And a sprite image is essentially that we're going to take the image, the input, or the xbatch, the input xbatch, and we're going to create a sprite image. And a sprite image is that it's going to have one image with all of the images in that batch that we send in. So let me see if I can bring up one example of that. So a sprite image of MNIST is going to, or this is fashion MNIST. So this right here, this is a sprite image. As you can see, it's a sort of a collection of many different images inside that single one. And that's going to be useful to send to TensorBoard so that we just have to send one image rather than many. And so that's what we need to do first of all. And I'm not going to do this, so I'm just going to steal it and I'm going to copy paste it. So this is stolen from this guy, Andrew B. Martin. And yeah, you can read through this. We're just going to use it. I'm not going to focus on what this does. So, but essentially it creates this sprite image. And basically it does some reshaping and some stuff and adds padding to get this image. We're going to create this define plot to projector function. And what we're going to send in is X, that feature vector I was talking about, Y, class names. We're going to specify some log directory as default. Let's just say default log directory. And then let's see, we're going to also get meta file, and we're going to specify metadata.tsv. All right, so this is going to make a lot more sense for what we're going to use them for. So first of all, we need to sort of make sure that the number of X dimensions is 4. Because what we're going to do is we're going to assume it's of this form where we have the batch size, we have the height, the width, and then the channels. And one thing that can be super frustrating is that you can't run this if you have a directory with this log directory already. And so what we're going to do is we're going to do if ospat is directory. So if there is a directory in log direction, that means that there's some old projector files there. So what we're going to do then is we're going to do shuttle.remove tree of that log directory. And then we're going to make that directory of that log directory. So essentially we're making it clean from scratch. So we're going to create a new clean fresh folder. All right. Then we're going to specify the sprites file. And that's going to be ospat join of log directory. And then we're just going to call it sprites.png. And we're going to do sprite is create sprite of X of the input data. Then we're going to do cmv2.imwrite sprites file. Sprites file, and then the sprite. All right. Then we want to generate the label names. So we're going to do that by doing labels is class names of y of I. So each respective integer target value for each training example. So I is a training example. Then we're going to do for I in range of int of y shape of 0, like that. Then we're going to write to that metadata.tsv file, and that's used for plotting in the labels in the projector. So we're going to do open ospat.join log directory and that meta file. That's what we called it. And then we're going to write to that one. And we're going to open it as f. So for label in labels, we're going to do f.write. We're going to do new line, and we're going to do .format label. All right. So we're just going to send in the label, and then we're going to make a new line. And that's just the structure TensorBoard wants it in. And now what I'm going to do is we're going to do the feature vector. So we're going to do if feature vector dot n dimension is not equal to 2. That would mean that it's not a feature vector. So that would mean that, for example, like we are doing it, we're sending in X batch 2 times. So if that is the case, then we're going to do print and we're going to do, let's see, note feature vector is not of form batch comma features. and then we can do reshaping to try and get it to this form. And then what we're going to do is feature vector is equal to tf.reshape, and then feature vector, and then feature vector dot shape 0, and then -1. All right, and then we're going to do feature vector is tf variable. So we're just going to convert it to a tf variable. And then we're going to do checkpoint is tf train dot checkpoint of embedding equals feature vector. And then checkpoint dot save, and then os path join log directory. And then we're going to specify embeddings dot ckpt. So we're basically saving that feature vector into the log directory, and then embeddings.ckpt. That's what TensorBoard wants it to be called. And then we're gonna set up a config that's gonna be write to the projector. So we're gonna config is projector.projector config. Embedding is config.embeddings add, and then we're going to do embedding.tensor name. We're going to specify embedding, and then we need to do this right here. We need to do dot attribute, and then variable name, variable value. And then we need to do embedding.metadata path. We need to do meta file. And yeah, if you feel this is a little bit clumsy, I mean, the code is kind of, there's a lot of code to do this. I wouldn't focus too much on the specific code. In PyTorch, for example, this is done in one line, literally one line. But in TensorFlow, this is a little bit more difficult. The embedding projector is usually done to project embeddings. Makes sense, right? So when we're doing it for images, we need to do it in this very convoluted way. But anyways, this is how we do it. But if you find a better way, then do comment. But this is the best way that I've found so far. Then we're going to do embedding.sprite.image path, and then we got to do sprites.png. So we're just specifying the image path, and then we're doing embedding.sprite single image dimension extend, and then we need to specify x shape of 1 and then x shape of 2. So we're specifying the height and the width. And lastly, we got to do projector visualize embeddings, and we're going to send in log directory and then the config, and that's it. So now hopefully, if there are no errors, this should run. And this is not right. So the error is that when we're normalizing the images, when we're creating these sprite images, we need to make sure that we don't divide by 255. And if we rerun it, we should hopefully obtain the correct pixel values now. And as you can see here, we have the images, and we can see right there, that's a dog, and then that's a boat or a ship. That's a horse, I think. And let's see what else. Yeah, anyways, you can play around with this. We have very few images here, right? So what you would probably want to do is you would change the batch size to something like 500. And if we rerun it, this is quite quick actually. All right, so what you need to do here, I think if you rerun it, you need to do sort of a new one. So if we rerun it now, and then we open it again in TensorBoard, sometimes this works, sometimes it doesn't, but now it works. All right, so now we get 500 images, and then you could do, use the TSNE, PCA, and this also, I've tried to make it general in the way that we could just replace this by MNIST, and we could just run it directly. And then if we now check it, all right. Yeah. Then of course we can't do this data augmentation. So let's remove the data augmentation completely. But we can't convert something to grayscale that's already grayscale. But other than that, I think this should be general in the way that we can just change that to MNIST, and then you would be able to project any type that you like. All right. Wait, there's one more thing actually. Yeah. So this is the last file of this one, but I want to show you the other thing too in TensorFlow Profiler. So TensorFlow Profiler is available since TensorFlow 2.2. And if you follow these tutorials, you know that I'm using TensorFlow 2.1 on the GPU. And so I can't use it. And it's actually necessary that you have a GPU to run. So what I did is I did it in Google Colab. And this is following very closely to one of their official tutorials. But so essentially, I'm going to just step through this, and perhaps you're watching this video in the future when you have, when you can easily install TensorFlow 2.2 and above with Anaconda. And so you can probably do this and create just a new file. So you wouldn't have to do this on Google Colab, but this works just to illustrate. All right, so first of all, we just have some imports right here. And then we got to do this pip install TensorBoard plugin profile. We're importing TensorFlow, and here we're making sure that we're running on the GPU. As I said, that's a requirement. And then TensorFlow, I think it works on the CPU, but for some functionality, there's a requirement that you do it on the GPU. So then we're doing TensorFlow datasets. We're importing MNIST, very similar to what you have seen throughout this tutorial. Then we're normalizing the image. We're doing some map and then batch. Then we create some very simple model. We do model compile. And then we create some logs. And they create these logs. This is from TensorFlow official tutorial using this datetime now, which is kind of clever, so that you would get a new log file every time you run it because the time has changed. So that's a pretty good way to avoid those errors. Instead of doing in the Projector way of removing the folder if it exists, then doing something like this could be easier, I think. All right, so then we have TensorBoard Callback, and we're just creating that. And all they're doing is doing this profile batch, and they're doing it 500 to 520. And so this is using it with TensorBoard Callbacks, but there are multiple ways you can do it if you have custom loops as well. I'm going to reference to that official tutorial in the description of this video if you want to check out more how you would do it. And then we're just doing model.fit, and again, using this TensorBoard callback. And then if we then do load extension of TensorBoard, so we open up TensorBoard and we run it with logdir equals logs, then we can get all of these different things. So we get an overview page. Maybe I need to rerun this. I think so. So we're going to factory reset runtime, and then we're going to run all. So then we can open up the profiler, and what we'll get is we have some different tools here. We have an overview page, and to be honest, I haven't looked into these in detail, but I'll show you just an overview of what they do. So this is the one that's perhaps the easiest to look at and the easiest to sort of understand. Here they give a summary of all the different parts. So you can see the timing for all of the different components of the training. You could also see different things, the placement. So let's see, number of TF ops executed on the host and the device. Not really sure what the difference between host and device is here. So again, I'm no expert in Tensor Profiler, but maybe someone can comment what this difference is. But other things you can see here is like the device compute precision. If you're using 16-bit, how many percentage of the computation is done on 16-bit? And then you can see some recommendations here, and this graph is quite useful as well. So you can see, for example, the input is highly input bound. 85% is waiting for input. So what we could do, for example, is now that we know that, we could do dot cache. What could we do else? We could do num parallel calls is autotune, and we could do that for both. So num parallel calls is autotune, and then we can do dot cache, and then we could also do dot prefetch, and we can do autotune dot prefetch, and we could again send in autotune. And yeah, I guess I'll just rerun this again. So runtime, run all, and we'll see if there's any difference in the output from the TensorFlow Profiler. Oh, by the way, this profile batch is between which batch in this says that you want to profile. So right here, we want to profile between the index batch of 500 to index batch of 520. So we're just doing the profile for 20 batches. So if you do it for too many batches, you could get out of memory errors. So that's why they recommend doing just 20 or 10 batches. And also not to put it in the initial batches, rather just to do it in the middle of training, because it could take some time to initialize things. All right, so let's again look at the profiler and see if there's any difference. So right now we can see that your program is moderately input bound because 16% is waiting for input. But that's a major improvement over the 85% that we just had. Let's see what more you have. Actually, you know what? You can play around with this yourself, and you can see, and I'm also going to reference to a TensorFlow official tutorial where they go into more depth on this TensorFlow profiler. But yeah, so for example, here you can see sort of the matrix multiply that is taking up 25%, the biggest chunk of the operation time. And then you have different things like trace viewer, and that's, you can get a very, very low level view of all of the operations done on the CPU and GPU, and you can see exactly what is taking up time. So this is a very, very cool tool. This is more of an introductory to that and just show you how to get it up and running. And yeah, so that's it. This is going to be a very long video. I can see that. And hopefully this video is at least useful in understanding TensorBoard. And yeah, thank you so much for watching the video, and I hope to see you in the next one.